Dear colleagues, sorry for these technical problems, and we will start with the second talk of Professor Evgeny Burnaev. The talk title is Generalization Bounds for Imbalanced Classification. Please, Evgeny.
Okay, so second, let me share the screen. Oh yeah, so okay, so here is it. Here am I.
Коллеги, sorry, Евгений, Анна.
Yes, here.
Анна, пожалуйста, добавьте Евгения выступающего, Евгений Бурнаев, и дайте возможность показать экран.
Yeah, I need a screen sharing capability.
Да, сейчас, секундочку.
Okay, that's it.
Проверьте, добавить.
Yeah, so it's okay. Oh, do you see my presentation?
Yes, please go to the full screen mode.
Okay, second. Okay, so Pavel, do you see my full screen?
Yes.
That's it, good. Second, I'll close all other applications so that nobody interrupt us. Yeah. Okay, hello everybody. Thank you very much for an opportunity to present my recent results on imbalanced classification.
Можно сделать экран побольше. Экран побольше, спасибо.
Побольше, just a second.
Теперь достаточно.
Okay, okay, so is it okay now?
Yes, it is okay.
Okay, good. So my name is Evgeny Burnaev. Just a brief introduction of myself. So in Skoltech, I manage quite a big group. We work mainly on applications of machine learning and deep learning for predictive analytics and 3D computer vision. We publish a lot, and also we collaborate a lot with industrial companies. And so actually the problems I'm going to discuss today, these problems originated as from some applications. So we were considering problems of rare event detection, and rare event detection can be formulated as an imbalanced classification problem. And we succeeded to formulate this as a strict mathematical problem, and now I'm going to present some theoretical analysis and outcomes of this theoretical analysis. So, motivation. As I said, we consider a binary classification problem statement. Practically, this means that as input to our algorithm, we consider some object. For example, we would like to classify whether a person or a bird is depicted on an image. We calculate some features for this image, and then using these features, characterizing the image, we would like to classify whether which object is depicted on the image, whether it is a person or a bird. So two-class classification problem. practice, the classification is imbalanced. For example, if we detect using some medical image whether a person has cancer or a person has no cancer, then the number of examples in the sample of images of persons with cancer, this number is often very 1% or small or even less. This is called often a minor class. So, the main goal of the imbalance classification is to accurately detect a minor class. However, standard classification approaches like logistic regression, support vector machine, decision trees, often these approaches treat all classes as equally important. However, in practice, if we don't take this imbalance into account, the resulting classification model is biased towards the major class, that is, the class for which we have a lot of examples. For example, if we predict an event occurring in just 1% of all cases, and the classification model always gives a no event answer, that the event doesn't happen, then the model is wrong only in 1% of all cases. So it's important to somehow to reduce the bias of the classifier to stress the importance of the minor class. And so in this work, we deal with possible class imbalance when constructing a classifier. For this, we use a weighted error, weighted risk, to stress the most important class, because we need accurate detection for this class. And the question is how to select an appropriate weight value to upweight a minor class, so to so that a classifier put additional attention on examples from the minor class. And so in order to do this, we define a weighted binary classification problem, and we obtain a generalization bound for a weighted binary classification, and from that generalization bound we estimated an optimal weight. The estimate is very simple. However, as I will show in according to the results of experiments, although the estimate is very simple, still it is useful in practice. So let me introduce some main definitions. As I said, results of computational experiments demonstrate usefulness of the obtained estimate. Before going into details with the problem statement, I'd like to introduce some useful definitions. The problem I'm talking about is related to estimation of generalization for a machine learning model. And as far as I understand, not all people who participate in the conference really work with such applications, with such models. So I need to introduce several important definitions. First of all, empirical Rademacher complexity. Let us denote by G capital some family of functions which map some input space Z to some interval AB. And let us denote by S a sample of fixed size. So each element of this sample belongs to that space Z capital. and the sample is fixed, just some elements from that space Z. And so empirical Rademacher complexity is defined as by this functional. So we here sigma I are Rademacher variables. They are IID random variables taking values plus minus 1 with probability 1/2. And so we calculate this empirical average and take the supremum with respect to all functions g small from the class G capital, and then we take expectation with respect to Rademacher random variables. This empirical Rademacher complexity characterizes the complexity of the function class G with respect to the fixed sample size, with respect to the fixed sample S. And also we'll need Rademacher complexity. So Rademacher complexity, actually, it is the average value of the empirical Rademacher complexity. We assume that on the set Z capital, there exists some distribution D. And so, because the empirical Rademacher complexity depends on the sample S containing M elements from the space Z capital, then the Rademacher complexity is defined as the average of all possible values of the empirical Rademacher complexity averaged with respect to the distribution D with respect to all possible samples S generated from this distribution D. Why do we need this Rademacher complexity? It's because when we prove the generalization bound, we use a very well-known, actually it is a classical result on empirical, following from the empirical processes. This result can be formulated as follows. Let G capital be a family of functions mapping from the space Z capital to the interval 0, 1. Then for any D greater than 0, with probability at least 1 minus D, each of the following inequalities holds for all functions G from the function class G capital. So either the average value of G of Z can be upper bounded by the empirical average value plus the Rademacher complexity plus this term which follows from the large deviation probability inequality. Or we can consider another variant of this bound when here we have the empirical Rademacher complexity. And because here we have an empirical Rademacher complexity, here this term here is bigger. So this is the classical result, and it will be used in when we prove the main theorem. But I just mentioned this in order to explain what is Rademacher complexity and what its meaning. Okay, and now let us finally formulate the binary classification, the weighted binary classification problem statement, and explain how we can obtain a generalization bound for it. So, problem statement. Let us denote by X capital an input feature space, and let us denote by Y capital output label space. So, as I already explained, we consider binary classification. So that means that for each object, we represent an object by some set of features. You can think about this like some characteristics of, say, image. And we would like to, and each object, it is labeled by some label which is either -1 or +1. Let us denote by F capital a class of binary classifiers. So this is some set of functions which maps input feature space to output label space. For example, the simplest class of such classifiers is the class of linear classifiers. So we have a linear separating hyperplane, and depending on whether this scalar product is positive or negative, we assign a positive or negative label to an object characterized by the feature vector x. Let us denote by P capital an unknown distribution on the space x, y. And let us denote by pi a prior probability of a positive class. So actually, when we collect a sample of objects, some proportion of these objects will belong to the class to the positive with positive label, and some proportion of objects will belong to the class with negative labels. And so pi is the prior probability of a positive class. That means that the joint distribution of x and y on the space xy can be represented as this sum. So this is the distribution of x given that the label is positive multiplied by the prior probability that the label is positive, plus the distribution of the feature vector x given that the label is negative multiplied by the probability that the label is negative. And actually, if pi is small or pi is close to 1, that means that the corresponding data set generated from such distribution will be imbalanced. And so we will have a lot of examples of one class and a very small number of examples of the opposite class. Let us denote by D capital a training sample consisting of n pairs of input feature vector xi and output label yi. And let us denote by R of f a Rademacher complexity of the function class, from which we would like to select the function which is our classifier. In order to estimate accuracy of the classifier, we use a 0-1 loss. So that means that if a real label is equal to y, and we predict a label for a specific object equal to y hat, then if predicted label and real label do not coincide, then we get an error, and we count this error in this way. Because we assume that our classification problem can be imbalanced, we need to somehow to stress the importance of the minor class, because if we, as I already explained in the beginning, if we have a small number of examples for some specific class, then when we train a classifier, when we estimate parameters of the classifier using some finite sample, it can happen that the classifier will not be able to correctly classify examples from the minor class. And so somehow we need to weight examples from the minor class so that we have reasonable accuracy of predictions for examples from the minor class. And so by U, we denote some fixed weighting function. In the next slides, I will provide a specific example of the weighting function we are going to use. By this term, we denote the theoretical risk. So f of x is some classifier from the function class f capital. We compare for different values of x the predicted label and real label, and we average this 0-1 loss with respect to all possible x and y generated from the true distribution P. Of course, we cannot estimate this theoretical risk because we don't know the true distribution P. And of course, if we know this true distribution P, F star is an optimal classifier equal to the which we can obtain by minimizing the theoretical risk with respect to the given function class. In practice, the only thing we can do is to calculate the empirical risk. That means that we that we use here the averaging with respect to the data sample, and so we estimate the average value of the 0-1 loss for a given classifier f of x with as I said, because for us it's important to get a good prediction for the minor class, we use here a specific weighting function, so that for examples from the minor class, this weight is bigger, and for examples from the major class, this weight can be smaller, so that when we estimate parameters of the classifier, we concentrate to minimize errors corresponding to the class of interest. And so the empirical classifier is equal to the minimum of the empirical risk over the given function class f capital. So what we want? Actually, we would like to estimate an upper bound for the XCAS risk. So XCAS risk is the difference between the theoretical risk and the empirical risk on the training sample. And we take the supremum over all possible functions from the function class f capital. Actually, this quantity, it characterizes to which extent the function class f is complex for a given classification problem at hand, characterized by the distribution P. In practice, it means the following. Let's imagine that we have two classes. One class is represented by red dots and another class is represented by blue dots. So if the function class f is too complex, then of course we can reduce the empirical risk very significantly, because we have a complex function class. So that means that we can model complex separating boundary between classes. But it's obvious that such separating boundary, given here by green curve, this separating boundary between classes isn't good. It is too noisy, so it overfits to the training data set. And for such function classes resulting in such separating boundaries, the XCAS risk will be big. XCAS risk for function classes from which we can obtain a result depicted here by the black separating boundary depicted in black. So for this case, the XCAS risk will not be so big. And so by controlling the XCAS risk, we can control the overall performance of our function class for a given classification problem. And what we would like to understand is how the XCAS risk depends on the weight, on this weighting function. So, as I said, in order to obtain explicit results, we will use an explicit expression for the weighting function. So we will weight positive class and negative class with two different weights in order to parameterize the weights for the positive class and for the negative class, we will introduce two positive weighting functions, g plus and g minus. So these are just some parametric functions of the parameter w, and the parameter w will be a parameter which we will tune in order to increase the weight for the positive class or decrease the weight for the negative class in order to balance the empirical risk to get the classifier with as small xks as possible. And so we proved that with high probability close to 1, so the delta is supposed to be a small number, the XKS risk can be upper bounded by the by this quantity delta, which is equal to this expression. So we have here three terms. This term results from estimating the theoretical risk for a given weighted classification, binary classification problem. This is the Rademacher complexity for the used for the considered function class, and this is the term resulting from the probability of large deviations. And so the question is how this upper bound depends on the weights. In order to investigate how the upper bound of the XKS risk depends on the weights, let us introduce one more assumption. So first of all, in this upper bound, we can control this term because this term depends on weights of the positive class and negative class, and also we term which also depends on the weights of the positive class and negative class. So by collecting the terms with the parameter w in the upper bound, we get this expression. This expression contains those terms which we can control. And in order to obtain an explicit algorithm to tune the weights, we will also assume that the weight g plus of w is equal to w. So this means that the weight for the positive class just linearly increases when we increase w, and the weight for the negative class it decreases like 1 over w when we decrease w. And so when we use such parameterization of weights for the positive class and for the negative class, we can minimize this upper bound on the XKS risk with respect to w. And we obtain that the optimal w is equal to this guy. However, because the probability alpha here, which results from the inequality, which results from the large deviation probability bound, so this term here is small when the sample size is big. And so approximately the optimal weight is equal to square root of 1 minus pi divided by pi. And pi is the prior probability of the positive class. So that means that if you have a sample, and for that sample we have like 10% of positive examples and 90% of negative examples, then pi is equal to 0.1, and we can estimate the optimal weight using this formula. And so the overall algorithm can be described as follows. So we weigh examples from the positive class with a weight 1 plus w, and we weighed examples from the negative class with a weight 1 plus 1 divided by W. So if W increases, this weight increases and this weight decreases, and vice versa. And by estimating the value of pi from the sample, we can estimate the optimal weight W star. And we use these weights with W equal to W star to weight positive and negative examples in the empirical risk. And so we minimize the empirical risk with such weights to construct a classifier. So this is the final algorithm. We estimate pi, we estimate W star, we weight positive class with this weight, with W equal to W star, and we weight a negative class with this weight with W equal to W star. And then we minimize the empirical risk with such weights to construct a classifier. We minimize it with respect to the considered function class. By the way, if we use such optimal weight W star equal to this guy, the upper bound of the XKS risk is equal to this term. So I just take the expression for the upper bound on the XKS risk and put instead of the functions, substitute instead of the functions g plus g minus, these values with W equal to this term. And so I get this upper bound on the XKS risk, and it's obvious that if the problem, the classification problem is imbalanced, that is, if pi is equal to 0 or pi is equal to 1, then the XKS risk will be close to 0 because this Rademacher complexity tends to 0 when sample size increases. And so that means that with such optimal weight W star, in case of imbalanced classification, we can guarantee to some extent that the XKS risk is very small. Okay, and now let me discuss an empirical evaluation of the algorithm. So actually, the estimates we obtained, these estimates are not very accurate because we used upper bounds, we used those inequalities resulting from the theory of empirical processes, and these inequalities are not very accurate. And so the estimate is quite crude. However, although the estimate isn't accurate, still, as I'm going to demonstrate, the estimate is quite useful in practice. So we expect that for the optimal weight value, a classifier achieves better accuracy on the test when being trained by minimizing the weighted empirical loss. And so we did the following experiments. The protocol of experiments is as follows. We consider different values of the weight W, like W1, etc., WK. We train a classifier, f of x, by minimizing a weighted empirical loss for a particular weight value from this set of weights. And we estimate accuracy of the classifier on the test set. So it is a separate sample which we didn't use when training the classifier. So we estimate accuracy of the classifier and find the weight for which accuracy is the highest. And we compare the best obtained weight from this set of weights with the theoretical weight calculated using this formula. So by this, we can understand whether the weight value which we found using experiments, we just tried different weights. So in this way we can find which weight is better. However, in practice, we don't want to make so many trials. In practice, of course, we would like to calculate the weight just by some formula and use it for when constructing a classifier. And so we compare the weight which we estimated empirically with the weight estimated by this formula. And so some results on two-dimensional toy problems first. This is the two-dimensional toy problem, so we just generated two-dimensional data from two different Gaussians. Unfortunately, the second, one of the classes is depicted here by yellow points, so maybe they are not very well visible, but okay, so you see that we have here two clouds, and we would like to construct a classifier separating these two clouds of points. Here I depict how accuracy on the test set of the constructed classifier depends on the value of the weight W. And so you see that the accuracy, the highest accuracy is achieved for the weight vector, for the weight value equal to 2. And if we calculate the optimal weight, it is also very close to the optimal weight obtained empirically. So we just estimated accuracy for all possible values for all possible classifiers with all possible values of the weight. This is quite computationally intensive task. And we see that the optimal weight is somewhere here, and it quite nicely coincides with the optimal weight estimated by the formula. This is another example. And so this is another artificially generated data set. And we see that, okay, the empirical optimal weight is located somewhere here, because here the accuracy is the highest. And the theoretical estimate of the optimal weight is quite close. Of course, this is not always the case. For example, for this data set, we see that the optimal weight should be somewhere here, because here the accuracy is the highest. But the weight calculated by the theoretical formula, it is quite far from the optimal weight. But okay, still this estimate is quite reasonable. So it's obvious that when we obtain the empirical estimate, we did a lot of assumptions which often are not valid in practice, and so it's not surprising why we get in some cases that the weight calculated by the formula doesn't coincide with the with the optimal weight which we find empirically. And now let us consider examples for some real-world problems. So we considered Penn Machine Learning Benchmark repository. So it's a set of empirical problems which you can find on the internet. These are data sets for classification tasks. We downloaded some data sets. These data sets are characterized by different input dimension and different sample sizes. And so we tested how the results depend on the imbalance ratio. So we take each data set, we take a positive class, and we undersample the positive class. That means that we randomly select some points from the positive class and just throw them away. We do this in order to consider real-world data, but with different positive class values of positive class share, because this corresponds to different values of pi. So we model the situation when we have different values of pi. And so to measure the performance of the method, we conducted 5-fold cross-validation, and as a classifier, we consider logistic regression classifier. This is an example of the data set called waveform. You see how on this plot you see how the accuracy of the classifier on the test set depends on the weight value. This is the optimal weight found empirically, and this is the theoretical weight estimated by the formula. Although the difference is quite big, but still the difference in terms of accuracy isn't so big. This is the case of the same data set, but here we keep more examples of the positive class in the sample. And so here these estimates coincide perfectly well. When the imbalance ratio is about 70%, we see that also these weights coincide, these estimates of the weight coincide quite well. And even when the imbalance ratio is very high, so we have a very small number of examples of the positive class and a very big number of examples of the negative class, still we see that these two estimates are in quite good correspondence. Even for very high imbalance case, you see that these two estimates are in quite good correspondence because the difference in accuracy between these two estimates isn't very big. This is another data set, and so the picture is quite the same. Although, for example, here the difference is quite big. I mean, the difference in terms of the value of the optimal weight and the value of the weight estimated empirically by considering all possible different values of the weight. But still, you see that in terms of accuracy of the resulting classifier, these two estimates are, do not differ too much. This is this is the case of the same data set, but for another value of the imbalance ratio. So the result, the qualitative picture is the same. And actually, I just wanted to mention that although the problem, the theoretical problem we considered seems very natural, still researchers didn't consider the case of the specific weighting scheme and didn't quantify the influence of the weighting on the overall classification performance. And so the results I presented, they are new, which is quite surprising because in principle the problem of binary classification, of course, I mean, there are a lot of research around the binary classification and its generalization capability and its generalization. So conclusion, we obtained a generalization bound for the weighted classification, and this bound resulted in a simple approach to estimate the weight for the weighted classification. That's it from my side.
Evgeny, thank you very much for a very interesting talk. And now it is time for questions.
Yeah.
Okay, we have a question.
Yes, please.
Natalia Mikhailovna, you could ask your question.
Evgeny, I think you don't know well the literature because similar paper was published by me and my collaborator, my brother.
Yeah, so please send me that paper because actually I did a quite significant literature review. Yeah, so for sure.
You can find it in my site. So the idea was exactly to recognize rare events. So when the density is very heavy-tailed, like in the case of cancer cases, and we use special weights to make the tail significant. To be able to distinguish between two tails, which one was lighter and another one was heavy.
But we are talking about different approaches. Actually, what I did, I obtained the generalization bound for the binary classification, and you're talking about a slightly different statistical problem, which rely on how the distribution tails of distribution for different classes go to zero. So these are just different approaches.
No.
Yeah?
Not at all. We minimize Bayesian risk, empirical Bayesian risk.
And I'm not optimizing the Bayesian empirical risk. I'm optimizing the I'm optimizing the XKS bound, which is another thing. So actually, when you consider the Bayesian risk, you assume that you know the distribution of classes, and we don't know the distribution of classes. We don't have this assumption.
Estimate. I said empirical Bayesian risk, but not Bayesian risk.
Yeah, but I don't. But in my estimate, I don't rely on this assumption at all.
I know.
That's it. So this is the difference. If you know, then this is the difference.
But you should mention us also.
Yeah, it's okay. For sure, I will mention. It's not a problem. Just send me the paper, and I will highlight the similarities and difficulties. Thank you very much. Yes, sure.
So
yeah, sure.
On page, it stands there on my homepage.
Okay.
So
but how the paper is called?
You can just Google Natalia Markovich homepage and you will find it.
Okay.
So, okay. The second question, may I ask?
Yeah, sure.
So, you speak about excess risk.
Yes.
So, in my understanding, excess means that you know the threshold.
No, I don't. So if you look, do you see the slides?
Yes, we can see your slides.
Good. So actually, XKS risk means that we have the difference between the theoretical risk and the empirical risk. That's it. And we don't have any assumptions on anything. The only assumption we have is that we know the function class and we know its Rademacher complexity. That's it. So I mean that from this point of view, these results are quite non-parametric in the sense that we don't assume a lot of assumptions on any assumptions on the probability distribution of data.
I also deal with non-parametric estimation, so like you. So and the last question is upon. I was a bit confused about real data analysis because when we deal with the real data, we never know what is optimal. What is this black point? You always
in practice we can estimate that black point. It's obvious that we can take the data set. We can divide the data set into two parts, train and test. Then we estimate the classifier using the trained data set. And we estimate performance of that classifier on the test set. And then we tune, and then we see how the accuracy on the test set depends on the weight, right? That's it. And this is exactly the black point. So we see for which weight value the accuracy on the test is the highest. This is the empirical estimate of the optimal weight.
Okay. And what is the empirical in this case?
This is the empirical estimate, and optimal estimate by writing optimal estimate, I mean the estimate obtained using this formula.
Okay, we have another question. Please, Vladimir Vasilyevich.
Okay, first of all, thank you very much, Evgeny, for a very interesting talk, for a very important topic, in fact. And your results are already published or available somehow?
I can send you the preprint, and I hope that they will publish in the proceedings of the conference.
Yes, so if you don't mind, please
Yeah,
send
sure,
me
of course.
the link. Okay, thank you.
So thank you very much, Evgeny, again. And now we turn to the next talk. I
Okay,
hope
so
this time.
let me stop sharing the screen.
Okay. So the next talk is the talk of Alexandr Vladimirovich Bulinski from Moscow State University. And Alexandr Vladimirovich will tell us about modern theory of feature selection and some of its applications. Please.
Thank you very much.
Excuse me, could you go to full screen?
Just a moment. Is it okay now?
Yes, yes.
Dear colleagues, I beg your pardon since there were problems with the internet. Now I will omit some details. Here you can see the plan of the talk. The role of mathematics in the nature exploration is illustrated as follows. In fact, this scheme is not so simple. To construct an adequate, in a sense, model of phenomena of the real life, usually one collects a number of observations and tries to discover some links between various objects or processes, which are not so evident. Moreover, it's a task to validate the model, that is to decide whether the description of the phenomena under consideration is appropriate, also in a sense. Rather rarely, one person performs all this work. The classical example is the discovery by Kepler of the planetary motion laws basing on observations accomplished by Brahe. A feature is an individual measurable property of an object under consideration. Some features can take discrete values, whereas others take values in a specified domain. In many situations, one studies a response variable y, and the goal is to study the relationship between y and a collection of variables x sub 1, x sub n. Thus, the problem is to determine a function f small. This problem goes back to the classical works by Legendre and Gauss. It was Legendre who introduced the least square method to solve such problem when f belongs to the specified class of functions. Note that at that time, the applications of this method were related to the study of the planet orbits in astronomy. Thus, the regression models arose. Linear regression, non-linear regression. There exist parametric, non-parametric, and semi-parametric regression models. Recall the following important non-linear model, namely logistic regression. It determines by the following formula. At the next slide, you can see several books devoted to the regression analysis and its application. Here you can see quite recent books on logistic regression, and here books on the general regression. Nowadays, one has to manage with huge arrays of data arising in diverse fields such as microarray analysis, test categorization, high-frequency financial data, phishing detection, and so on. Such data have extremely high dimensionality, big data. The problem of finding the relevant, in a sense, features among the huge collections is of great importance. For instance, to construct an interpretable model of the phenomenon under consideration. Thus, in contrast to the classical linear least square method, one doesn't use all features for a model construction. The discovery of the structure of DNA is one of the most famous scientific events till nowadays. Each helix of the human genome contains more than 3 billion nucleotides. Only in the 21st century, the researchers have read such enormous sequences of letters belonging to the set ATCG. Now it's possible to specify the location of genes and single nucleotide polymorphism, SNP, on this helix. The damage in the human genome structure leads to complex diseases. The challenging problem in genetics is to identify a collection of steps which provoke the complex disease. In contrast to simple disease, the impact of each step can be small and only the interplay of certain damages of DNA structure can be generous. Here we have the so-called effect of epistasis. A single-source stochastic model illustrating this effect can be found in a paper by Bulinski and Kazhenin. To encourage researchers on this difficult way of data analysis, it's worth to recall the following phrase by the Nobel Prize winner Wigner. He wrote, "It's true that if there were no phenomena which are independent of all but a manageably small set of conditions, physics would be impossible." In machine learning and statistics, feature selection, also known as variable selection or attribute selection, is the process of selecting a subset of relevant features for use in model construction and for other purposes. In fact, the feature preferences can be represented as a ranking, a weighting, or a subset. Feature selection techniques are used for three reasons. In terms of availability of label information, feature selection technique can be classified into three groups: supervised methods, semi-supervised methods, and unsupervised methods. The literature on feature selection is vast. Next three slides show 24 recent books devoted to feature selection. The mentioned books and also the numerous papers devoted to development of the feature selection techniques explain why we will only mention various research areas and consider some important problems. Discussions on feature selection usually center on two technical aspects: search strategy and evaluation criteria. Algorithms designed with different strategies broadly fall into three categories: filter, wrapper, hybrid, or embedded ones. Often filters are used in two-step procedures as the first step. Trivial example. The variance filter uses the estimated variance of a feature xk as its score. This filter is employed to get rid of features that only consist of small noise and therefore have small variance. It has sense when the features are measured on the same scale. In this quite recent paper, 16 high-dimensional classification data were considered, as well as 22 filter methods. The authors concluded that there is no group of filter methods that always outperform all other methods. Wrapper methods are subdivided into exhaustive, heuristic, random search. Embedded methods are quite similar to wrapper methods. The difference is the following. An intrinsic model building metric is used during learning. Few examples. Here you can see some well-known filter methods, wrapper methods, and embedded methods. To illustrate wrapper methods, we recall the sequential forward selection procedure. Let X be the original vector of features, and J be a measure of quality of a subset S of S. Starting with empty set, one feature is added at each step. Mainly, we consider it a feature with label I star, which is defined in the following way, and often Y is a response variable dependent on X, then J of S can characterize the quality of approximation of Y by X of S. In general, the exact value of J of S is unknown. This problem is discussed in the previous interesting talk by Professor Burnaev, since we do not know the distribution of xy. Thus, instead of J, one uses its approximation evaluated on a part or parts of the training data, consisting of IID random vectors. And let J hat be an estimate of J constructed by means of these observations. Thus, for a fixed T, we can sequentially search random index I star by means of J hat instead of J. The sequential feature selection is run to the end, and the result is an ordered collection of random indices, that is, features. If a subset of R features is required, then we take this collection. the important problem arises whether I is close in a sense to I star. Now we mention the recent paper by Bio and collaborators devoted to accelerated gradient boosting as an example of embedded methods. This is the collection of observations, and the learning task is to construct a predictor f that assigns a response to each possible value of the independent random observation xn+1. In the context of gradient boosting, the general problem is addressed by considering a class f0 of elementary functions, f small, called the weak of base learners, and by minimizing some empirical risk function. Here you can see the so-called additive solution. A function L is called the loss. It's assumed to be convex and continuously differentiable in its first argument. It measures the cost carried by predicting f of x when the answer is yj. Here you can see the classical examples of the loss function. The theoretical version of empirical risk is the following. Bio and co-authors consider the problem of minimizing C of f over a given set linear whole of f0 belonging to the space √2. The functional C is differentiable at any f in the direction g, with the differential where the nabla C is given by this formula. Suppose we have at steps t a function ft and find ft+1 to add to ft capital, so the risk decreases at most for some small value of w. One approach might be to take ft+1 in the following way. However, since the new function must belong to f0, this is in general not be a possible choice. The strategy is to choose the new ft+1 by a least square approximation of this function. In the empirical setting, when C is equal to Cn, one has the following formula. And iteration ft+1 together with indicated approximation of f small form the core of the gradient boosting. The essential difference is the presence of the companion function sequence gt, which slides the iterates ft according to the certain recursive parameters lambda t and gamma t. Bio and collaborators combine gradient boosting and Nesterov's accelerate descent. In quite recent paper by Gerber and co-authors, the authors propose instead of solving discretization, feature selection and prediction problems separately, to employ the introduced scalable probabilistic approximation algorithm to solve them simultaneously. The applications are provided to classification and prediction problems from natural sciences. There are many complementary approaches concerning the prediction of response variable and the identification of the significant combinations of factors. Such analysis in medical and biological investigations is included in the special research domain called the genome-wide association studies. Next two slides show various methods used in GWAs at 2006 and 2011. Here the still life. In this picture, you have more different methods, and now one can indicate more than 100 various methods, so it's difficult to mention them on a single slide. We recall several methods related to regression analysis. Here is the famous list absolute shrinkage and selected operator. We can write this problem in Lagrangian form with penalty function fp and a tuning parameter lambda. Elasticnet penalty, smoothly clipped absolute deviation penalty. That's the key idea of these methods is to specify a collection of beta j which can be neglected, consider it as zero. A recent survey by Wang is devoted to methods in feature selection and penalized regression. For further information, we refer also to the following well-known books. Now we turn to non-regression models and consider the development of multifactor dimensionality reduction MDR method. This non-parametric method was introduced in the paper by Ricci and co-authors for binary response variable in the framework of identification of genes responsible for the complex disease. The review by Goula and co-authors demonstrates great popularity of this method. More than 800 papers published between 2001 and 2014 were devoted to extensions, modifications, and applications of the general idea suggested by Ricci and co-authors. Here you can see the picture illustrating this method. The researchers use different terminology for specified approaches leading to dimensionality reduction of features. For instance, the following method were proposed. We now concentrate on MDR-EFE error function estimation method, which was introduced and studied in a series of papers by Bulinski and co-authors. Let x and y be random vector and binary random variable. We introduce an error function as follows, and we wish to determine the quality of y approximation by f of x. One can describe the class of optimal functions in the following way, where gamma is the threshold. The law of xy is unknown, therefore one cannot evaluate error f for a function a. Thus, the inference concerning the quality of approximation of y by fx is based on statistical estimates of error f. Here we can see the ID observations and employ the so-called prediction algorithm determined by this function. For some integer k, we consider the partition of the set 1, so on, n, capital by sets sk, and introduce error head by this formula using the k-fold cross-validation. Using the strong law of large numbers for arrays, not for sequences, we establish the criterion for the following relation validity. In our papers, it's shown how one can use such estimates to identify the collection of relevant vectors. Any collection, xk1, xkr, is called relevant if for any x, the following relation holds. Here is the definition of some estimates, and we can introduce FPAM1MR head by this formula, where gamma head is a strongly consistent estimate of the threshold gamma, constructed by means of observations. We can prove that this limiting relation is true, almost sure, where FM1MR is given by this expression. Thus, it's important that with probability 1, for any positive epsilon and each collection M1, MR, we have the following inequality. Thus, for a given R, it's natural to choose among factors x1, xn a collection xk1, xkr, leading to the smallest estimated prediction error, error head. Moreover, in our paper and our joint paper with Alexandr Rakitko, the symptotic normality of the regularized versions of the introduced statistics was proved, and in two later papers, a non-binary response was studied. Bulinski and Khatskevich developed MDR-EFE method for stratified samples. It's important for the identification of relevant factors having impact on a rare disease. Rakitko proposed a version of MDR-EFE method involving selection. An important subject is the development of algorithms for structured features. Usually, one is assumes that all features are known in advance. However, in certain modes, the candidate features are generated. Such features are named streaming ones, and the streaming feature selection arises. We refer to the following papers. Now, we concentrate on methods involving information theory. In contrast to the correlation coefficient, one applies the basic information theory concepts to identify nonlinear links between random variables. In this regard, we mention entropy, mutual information, conditional mutual information, and various divergences, for instance, the Kalbeck-Leibler one. There exist various definitions of entropy. We recall one proposed by Claude Shannon. Here is the definition for discrete random variable, and this is the so-called differential entropy when a random vector x has a density f small. Here you can see two other popular definitions, the Renghi entropy and Thales entropy. We mentioned in passing the important contributions to the entropy concept developed by Boltzmann, Gibbs, Planck, Kolmogorov, Sinai, and Kolev. Recall that the Kalbeck-Leibler divergence for probabilities P and Q is defined by formula. This is the particular case when there exist densities for these measures. Now we turn to the mutual information. That is, we consider the Kalbeck-Leibler divergence between the joint law of x and y and the product of their distributions. Note that this divergence is zero if and only if x and y are independent. As mutual information can measure relevance, this quantity is currently used in literature for performing feature selection. The well-known minimum redundancy criterion proposed by Penn. Here you can see the corresponding definitions. Clearly, one has to apply statistical estimates of the mutual information. The entropy, Kalbeck-Leibler divergence information play important roles in such domains as statistical inference, machine learning, computer vision, network security, feature selection and classification, physics, biology, and finance, among others. We refer to the following interesting papers. In a series of papers, the entropy estimate was studied and applied. Moreover, estimators of the Rényi entropy, mutual information, and the Kalbeck-Leibler divergence have appeared. However, the authors of the paper, Pal and collaborators, indicated the occurrence of gaps in the known proofs concerning the limit behavior of such statistics. This issue has attracted our attention and motivated our study of the declared asymptotic properties. Thus, in the paper by Bulinski and Dmitry, the new functions were introduced to prove under wide conditions asymptotic unbasedness and autoconsistency of the Kazachенko-Leonenko estimates of the Shannon differential entropy. Moreover, we develop our approach to grasp the conditional Shannon entropy, Kalbeck-Leibler divergence estimation, and the mutuals. We refer to the following works. We refer also to the chapter in the book by Biot and De Vroy, recent works by Barrett and Delator and Fournier, where important results on the convergence rates for the Kazachенko-Leonenko estimates are established for densities. We employ various techniques. The careful analysis of conditional distributions of the specified random functions, theorems concerning weak convergence of random vectors, convergence of certain integral functions, and so on. The great writer Chekhov wrote in 1998, "You can't put a loaded gun on the stage if no one wants to fire." Note that this is the correct translation of the well-known phrase of the great writer. Today we discussed the logistic regression model and the mutual information concept. This is the just time to employ them. Consider a mixed model where a response variable y takes and I say m. Assume that the following relation b and mu and lambda holds. Note that this model comprises the classical logistic regression. For this model, we can write the radon-nickel and therefore the mutual information is provided by this formula. One might conveniently write later formula in three ways, provided that the expressions make sense. If an function is finite, it doesn't imply the finiteness of integrals of sums. Thus, we have the following formulas. Here, the Shannon entropies of x, y, and x, y vector are employed as well as the conditional Shannon entropies of x given y and y given x. One can prove that in the framework of y is always finite, and this is the great advantage, and relation 3 holds. However, to guarantee the validity of formula 2, one has to impose certain conditions. For a mixed model, the estimate of I involving formula 2 was proposed by Kaelje and co-authors. This is not the general approach. I've just explained why the formula 3 is more attractive. However, these authors didn't analyze asymptotic properties of that estimate, so we accomplished this task. Moreover, in a quite recent paper by Bulinski and Khatskevich, the new estimate of the conditional entropy was introduced in the framework of a mixed model, and under Y conditions, its asymptotic unbasedness was made and L2 convergence was proved. Here is the definitions of these new estimates. I understand that we haven't enough time to explain all details. I only would like to say that in contrast to the well-known Kazachenko-Levin estimate, we employ the different approach. The principal role is played by the random variables. Namely, it's necessary we construct some random balls with specified random balls, and in that random balls we find sub-collections of random variables. Here you can see the following result. Note that conditions are quite simple. Notice this logarithm of distribution of features x. Then we have the asymptotic unbasedness. And L2 consistency we obtain if we replace the previous condition by this one. The proofs of our results devoted to entropy, mutual formation, and the Kalbach-Leibler divergence are quite involved and take more than 100 pages. Thus, I decided to show you only one of them. Behar and collaborators provide new theoretical results concerning the conditional mutual formation. The author applied the results for forward and backward feature selection algorithms. Now we consider some simulations. We compare our estimates of mutual information with known ones using the following regression model. Namely, we compare two options. We consider light tails and heavy tails. And you can see that our estimate at line has certain advantages among all known 5 estimates of mutual information. Verma and co-authors propose a collective feature selection approach to select features that are in the union of the best performing methods. And they compare MDR method and gradient book, especially for identification of epistatic effects. Now, we turn to stability of feature selection. The stability of a feature selection algorithm can be defined in various ways. It would be desirable to take into account a stochastic nature of data under consideration and also the randomness of data sampling. One can say that an algorithm is unstable if a small change in data leads to large change in the chosen feature subset. This idea is simple. However, its realization demonstrates a number of different approaches with different motivation and justification. Here, I would like to describe the general feature selection algorithm, not sequential feature selection. And as a result, we obtain a collection of sets, FIR. Now we address the following questions. How similar these collections are? Well, this similarity can help to choose the final set of relevant features. The output of a feature selection algorithm can be represented as length n with one at the if position if each feature has been selected, otherwise zero. The relative Hamming distance between two subsets is defined as the number of bits they have in common divided by the length n of a string. It's interesting that Kumcheva proposed consistency index, and here is the explanation why this index is natural. This normalization was called the correction for chance. The important idea of subsampling employment goes back to Meschenhausen and Burnaev. The problem of feature selection stability is important not only for mathematics itself, but also for applications, e.g. in genetics. In the paper by Nogueira and co-authors, the authors consider 15 different measures used in the literature to quantify the stability of feature selection algorithm. Various important properties of such measures are compared and new measures is introduced. There are two different approaches, similarity-based approaches and frequency-based approaches. Here you can see of various measures, and using the random matrix Z, it's possible to observe frequency of selection of feature xj, and Nogueira and co-authors proposed the new stability measure using this matrix Z. And it's very interesting that this measure, in contrast to the previous ones, possess 5 desired properties for any stability index. Some applications. The recent survey by these authors is devoted to the feature selection methods in medicine. Namely, the authors concentrate on the image analysis and pattern recognition, the medical signal processing, and DNA microarray data analysis. For this purpose, one uses X-ray, computed tomography scans, magnetic resonance images, and other sophisticated techniques. The method involves the representation of Bayer signals by means of Fourier and wavelet basis functions and autoregressive parameters. The representation can be viewed as a feature vector that can be further analyzed to identify the most representative features and to reduce the dimensionality of the final data set. In this regard, we refer also to the quite recent and actual paper by Sun and collaborators. The author proposed an adaptive feature selection guided deep forest COVID classification based on chest computer tomography images. On this way, it's possible to separate COVID and community-acquired pneumonia, CAP. Here is the approach by these authors. Also, the authors compared their method with the following machine learning methods: logistic regression, support vector machine, random forest, neural networks, in order to measure the classification performance for evaluation metrics. 4 evaluation metrics are employed, for instance, classification accuracy. And these authors show that their method is a little bit better than previous ones. Genome-wise association studies have successfully identified risk loci for a vast number of diseases. We refer to this word. GWS can lead to the discovery of novel biological mechanisms. For example, in the quite recent paper, 6 previously unknown loci associated with certain problems were identified. We refer to the following recent publications. Moreover, Feature selection methodology is used now in financial problems. We refer to these recent publications. The development of deep learning framework with two-stage feature selection for multivariate financial time series forecasting is considered by new and co-authors. Conclusion. The main goal of the talk was to provide the survey of several important branches of the feature selection theory. We have discussed various domains belonging to feature selection theory and its applications. Note that now the most part of the papers are devoted to construction of different algorithms, analysis of simulated and real data. Also, we try to establish the theoretical results concerning the development of MDR method and statistical estimation of the Shannon differential entropy, conditional Shannon entropy, and the Kullback-Leibler divergence, which play important role in many applications, including feature selection. We have seen only the top of an iceberg. Now we mention some research directions in feature selection which are important and deserve a special analysis. Causal inference, image classification medicine, feature construction. If the origin features are not informative enough to achieve promising performance, feature selection can be not efficient, thus feature construction may be useful. Multi-steps algorithm, parallel algorithm, development of a stopping criteria for algorithms, random graphs, forests, and so on. We recommended a number of recent papers attention.
So thank you very much for this nice talk, review talk, and it is time for questions, comments, questions. Vladimir Vasilyevich, you have raised your hand. Do you have question?
Sorry, it was from the first talk, but in any case, I repeat maybe my question, similar question. So, talk was really fundamental, I would say. And this review was prepared for publication somewhere, or it was prepared just for presentation during this conference?
I think that this talk, namely the full version of the excerpt, will appear in the special Springer volume.
I see. Oh, okay, I understand. Thank you very much. But it was really fun.
Thank you.
So, any more questions, comments? So there is no questions, and in this case, I would like to thank our speaker, Professor Bulinski, again. And now we have a lunch break, and we will meet again at 2:30. Thank you very much.
Thank you.
Welcome everybody to our afternoon session. So today we will have 5 talks during the session and 1 break. And the first speaker of the session will be Natalia Markovich from Trapeznikov Institute of Control Sciences, and she will speak about extremes of sums and maxima with application to random networks. Please.
Thank you for introducing me. My work has a long history. Was motivated first by application in random networks. Now this application is very much in big interest of big community. I think with respect to internet and many other examples of network application. And well known that PageRank can be considered as index of node influence, and less known is the so-called max linear model. It is a maximum analog of PageRank and also can be considered as such node influence. And I consider already several years how to find the tail and extremal indices of PageRank and max linear model. And this work is an extension of my results joined with Igor Rodionov and published recently in the journal Extremal. And I aim to consider these results further for weaker assumptions, and then to apply the obtained theoretical results to random networks. What is a random network? Each node pair in a random network is connected with some probability. So it means that node degrees are random, and in degree, out degree, such values are also random. And this is due to the dynamical changes of the networks in time and space. And here I demonstrate one example, Facebook graph. PageRank is well known by Google definition as such a ranking characteristic of the node. But there is another approach, and PageRank is considered from another perspective as the index of a randomly chosen web page. This is a vertex on a web graph. It may be considered as a root node of a Galton-Watson tree with random in and out degrees, and it may be modeled as a random variable R, which is a solution to the fixed point problem in Formula 1. This such a formulation of PageRank is considered in many papers by some fixed number of authors, and here I give the names of these authors, and everything published in applied probability journals mostly. And the main assumptions is that all the sequence Rj are ID copies of R, independent of Q, N, and the weights Rj. Then, in more or less in all these papers, by little bit different assumptions, additional to assumptions A, it was proved that the stationary distribution of R is regularly varying, and its tail index is determined by the most heavy tail distributed term in the pair. Both N and Q are assumed to be regularly varying distributed. Then the further development of this problem was given in the paper of Asmussen and Foss in 2018, when they consider a multivariate version of 1. So it means that we can assume that this Rm of k is distributed the same way as Rk, and Nk is the number of type K children of a type E ancestors. The unique solution of 1 is proved to be intermediate regularly varying if Q and or N has an intermediate regularly varying distribution. So it's considered for the more general class than the regularly varying. Then a max linear model can be obtained by substitution in one sums by maxima. That was first considered in Esquivel and Kluppelberg paper, but was published a bit later than Yelenkovich and Alvera Kraviota paper. It was several years in archive where I could maintain it because I think it was some problems with publication. Under the same assumptions, the asymptotic behavior of R is power law. This is a definition of power law distribution. H is constant, alpha is positive, and asymptotic equivalence is understood as x tends to infinity. Our objective is to consider tail and extremal indices of sums and maxima of random number of terms n. So I consider only sums and maxima of the right-hand side of the later equations under more general assumptions than assumptions A. And I aim to find conditions when the sequences of sums and maximum have the same tail and extremal indices. Let me recall again what is extremal index. The definition was given in the book of Leadbetter et al. A stationary sequence with distribution function f and maximum is said to have extremal index. This is the value inside the interval 0, 1 if for each constant tau there is a sequence of real numbers. This threshold that depends on this tau such that these two limits hold. The ID random variables have extremal index equal to 1. The converse may be incorrect, and extremal index that is close to 0 implies a kind of a strong local dependence. It's also well known that reciprocal of extremal index approximate the mean cluster size, where we understand cluster as some consequent observations exceeding a sufficiently high threshold. A formulation of the problem. Let me formulate the problem like it was formulated in my joint paper with Igor Rodionov. And then I will give new assumptions and new results. So this is a doubly indexed array of non-negative random variables in which the row index n corresponds to time and the column index I enumerates the series. On the same probability space, a sequence of non-negative integer random variables and n is indexed is existed. Let y and e be a strict sense stationary sequence with extremal index theta I having a regularly varying tail. Here, in part of polynomial term, we have a slowly varying function. Examples of slowly varying function positive constants, logarithm, repeated logarithms, things like that. And the tail index is assumed to be positive. So we have no assumptions on the dependent structure in I. So the column sequences can be arbitrarily dependent. This is important. So for better understanding, let me show you this matrix. This is a double indexed array and provided by 0 because n is random and not necessarily increasing sequence, and each column has its own tail index and own extremal index. It doesn't mean that it's stationary distributed, but each column has its own distribution because even if tail index are equal, each column has its own distribution because of slowly varying function. Can be different. So, and we take what we make. We take maximum and sums over rows, like this, and consider the new sequences that are built by these sums and maximum. Then we consider the weighted sums and maximum. Here, these weights are expected to be positive constants, and the sequence of sums and maxima are taken over rows. The tail and extremal index of indices of maximum and sums were found in this paper. But first, I have to mention another paper that motivated me for this work. It was in the thesis and in the paper of Anna Galdaeva, who considered the same random sequences, but of a fixed length. And she expected that, assumed that the sequences have a power type tail. So, in other words, she considered such a class with the positive weights that is narrow, of course, than our consideration, where we consider more general case regular revarying. And then she proved two theorems that we somehow used also for our proofs to go further to the random case when we have random length. Then a part of that we have to implement some restrictions on the slowly varying function. So for all a larger than 1, sigma larger than 0, there exists x0 depending on these constants, such that for I more or equal to 1, we have such a bound for such x that exceeds this level. So this is very principal restriction that we couldn't avoid. N has a regular varying distribution, despite this is in reality integer value. But this is well-known representation, well-known fact that is motivated in many papers. There is a minimum tail index K1. Then the rest of the tail indices has an infimum K. Ln is expected as a function of n is sample size, and this degree is also bounded by some function of K and minimum tail index. Then an arbitrary dependent structure between this sequence and this sequence is allowed. So this was the main restriction of this paper. So we have only unique column with the minimum tail index. It can be 2 and 3 and etc. Only one. And then for this unique column with the minimum tail index K1, we prove the following two theorems. Let K1 is less than K. Then all these restrictions regarding the bounds for slowly varying function built. Then the sequences of weighted maximum and weighted sum have the same tail index K1 and the corresponding to K1 extremal index theta 1. Then the next step we took instead of L1, the sequence of lengths, we took the random length n. And for the same restrictions regarding slowly varying functions, this restriction is for the representation of n distribution, and this restriction for this y distribution. We suppose again that K1 is less than infimum of all other tail indices, and expect also, this is important assumption, that n has a lighter tail than this sequence. The sequences of maximum and sums have the same tail index and the same extremal index. Now I consider the columns that have the smallest tail index K1, and D is larger than 1. Again, I assume that K1 is less than K, but infimum is taken already for the rest of columns. If we consider on this schematic matrices, then this is the assumption of our paper with Igor Rodionov, and here is my assumptions. So I assume that X number of columns have minimum tail index, but extremal index can be different, and there may be also random. Then let me formulate so-called independence condition, assumptions A1. The stationary column sequences, I speak about the first D column, are mutually independent and independent of the rest of columns, this part. Denote the is column maximum as the following, MNI. Let me formulate new theorem 3 for the maximum and for the sums. Again, yeah, I take the length first as a function of n. Let we have the same assumptions regarding the uniform upper bound for slowly varying function. For the rest columns from d plus 1 till n numbers, then maximum and sums have the same tail index. Then if in addition the independence condition holds, then maximum and sum have the same extremal index. So if d equals to 1, then we can easily get again theta 1. If A1 doesn't hold and d equals to 1, then we have this extremal index. But it may not exist if d is larger than 1. Assuming for these assumptions that A1 doesn't fulfill and D is larger than 1, all elements in pairs in the columns have the same mutual condition. That's what we assume, mutual dependence. And we can assume that this sum is the smaller order than this one. In this case, the sums and maximum have the same extremal index with index d. One can rewrite them with regard to the is column and get the same statement premier at the end. The next, let the sets of slowly varying functions are the same as before. Assume that d is a bounded discrete random variable, so I consider the situation when we have a random d, and this d is bounded by minimum of c and n. C is some constant larger than 1, and d and the sequence are mutually independent. Then again I assume that number of terms in the sums and maximum has a lighter tail than this one, and then maximum and sum have the same tail index, but the extremal indices do not exist. This is not typical situation, but there are many processes that have no extremal index. Otherwise, would be very good for us, and we could always represent the limit distribution of maxima by means of extremal index. But this situation gives us example when extremal indices do not exist. So application to random graphs and networks. I again recall this matrix, but where the weights are the same, not the Z1, Z2, Z3, but always same. This is a mimic of Google definition of page rank. U1 is called in this terminology of Google page rank as user preference. And this, in my consideration, is also a random variable that may be also regularly varying distributed. And then I consider again the sums and maxima over rows, and expect that in contrast to the papers that were mentioned at the very beginning, here these terms are not necessary IID, and also the mutual independence between this and this and n are not assumed. And this is a big difference with regard to the well-known papers. Then each column again has its own tail index, own extremal index. Might be possible that fixed or random number of columns have the same minimum tail index. The last column that has the meaning of user preference has the extremal index equal to 1 because the user preference is independent for different users. And tail index can be also positive value beta. Let me show this schematic graph. This graph has nodes from different communities. The term community is well known in random graphs, and roughly speaking, one can understand that community is a group of nodes that are well connected inside this group and less connected with the rest of the network. And there are many methods how to select these communities, how to detect it quickly, rapidly. There are many papers devoted to the definitions of community, different definitions and methods how to select it. But for me now it's important that followers of one node, these are followers that look, this seems to be, it can be, for instance, a web page that are looking for from different nodes from different communities. Let's say this web page with Volkswagen car or sport news that can be interesting from people from different communities. And by the black node, I label nodes with the minimum tail index. So I call it dominating communities with the most heavy tail distributed influence indices. And other communities are marked by open circles and filled circles. This graph can be also disconnected. This also be possible. So, and then each node of this graph can be considered as the root of the directed graph of its followers.
Natalia, we have only 1 minute.
1 minute. So, and then in our terminology, the column sequence is the community, the row sequence is the first generation of followers, n is in degree, so the number of non-zero elements in the row, and the column dependence come from overlapping community. So at least one neighbor of the root nodes belongs to one of the deco, the most heavy tail dominating community. And then I formulate the theorem. Page ranks and max linear models of n root nodes have the same minimum tail index as one of the most heavy tail distributed communities within a random graph associated with the roots as n goes to infinity. The extremal index is equal to the extremal index of the most heavy tail distributed community if the letter is unique. It is calculated by formula 10, assuming extremal indices of the most heavy-tailed communities if the letter are mutually independent and independent of the rest of communities. Or it may not exist if the letter independence condition is not valid. So, and practical assumptions are the following of this theorem. The node influence indices within non-dominating communities are allowed to be non-stationary distributed. All elements of the dominating communities have to be regularly when distributed, and dependence between communities impacts the extremal index of page rank and Maxima models. So our approach can be used to simulate an enlargement of graphs or evolution of networks with given values of tail and extremal indices of the node. And this would be the next topic of my research. And here I demonstrate two papers that motivated this research, my present research. Thank you very much for your attention.
Thank you very much for an interesting talk. Unfortunately, we don't have any time for questions because our schedule is too strong. So,
Dmitry, sorry for interrupting. Just technical thing. Анна, добавьте, пожалуйста, в список выступающих Хатскевича, Владимир.
Yes, please.
Да, сейчас.
Okay, so I think we should thank Natalia Markovich once again, and then I think we should proceed to the next talk.
Наталья Михайловна, пожалуйста, остановите демонстрацию экрана.
Спасибо. Все, да?
Да.
Все, права на выступающего есть.
Please share your screen. Okay, so we have some bad noise. So I think we should continue. Next speaker, our next speaker is Vladimir Khatskevich from Air Force Academy, Chukovsky Academy in Voronezh. So he will speak about the law of the large numbers and linear regression of user random variables. Please.
Sorry for my bad English. Fuzzy random variables appeared as a branch of fuzzy mathematics in papers.
Could you speak louder, please?
Quaternack, Namias, Purian-Ralevsky, and etc. Fuzzy random variables are widely used in financial mathematics for testing decision theory and others. In particular, the mathematical model of a random experiment with fuzzy outcomes is interpreted as a fuzzy random variables. The current state of the theory of fuzzy random variables is reflected in Nguyen-Wu, Fundamentals of Statistics with fuzzy data, Verti, Statistical Method for Fuzzy Data, Shvedov, Estimating the Means and the Covariance of Fuzzy Random Variables. We will use an interval representation of fuzzy numbers and match each fuzzy number with the set of its alpha intervals. Definition. The set alpha level of fuzzy number A with the membership function mu A of x is defined by the relation. Denote the left border of the interval A minus of alpha and the right one is A plus of alpha. So A alpha is equal A minus alpha, A plus alpha. Denoted by G0 the set of fuzzy numbers in the interval representation of which the functions A minus alpha and A plus of alpha are quadratically summable. Let the fuzzy number Z corresponds to alpha levels Z alpha with alpha belongs 0, 1. For the fuzzy numbers Z and U from G0 we define a quasi-scalar product by the formula 1. And the quasi-norm Z is in the form in this form. This is a new form of quasi-scalar product for fuzzy numbers. Another definition for the scalar products of fuzzy numbers was used by Neither in 2006 Kalabi, in 2009 Shvedov, 2016. Expression 1 resembles the scalar product of vector function Z plus of alpha, Z plus of alpha, Z minus of alpha, and U plus of alpha, U minus of alpha. Take place the following properties of quasi-scalar product 1. Note the property 2 holds for constants C1 and C2 if the product C1, C2 is positive. It is convenient for us to determine the distance between the fuzzy numbers Z and U from G0 with the sets alpha levels this and this by formula 2. This kind of a distance was previously used, for example, in the paper of Bargelia, Pedrish, and Nakashima in 2007. Let omega sigma p be a probability space. The measurable map x from omega to G0 will be called a fuzzy random variable if G0 is the set of fuzzy numbers. Consider the intervals of alpha levels of fuzzy random variables x and fixed omega, namely x alpha of omega is equal expression where mu x of omega membership function of a fuzzy number x of omega and alpha belongs 0, 1. The interval x alpha of omega, imagine x alpha of omega is equal x minus, and x plus, with the boundaries of x minus of omega alpha and x plus of omega alpha random variables. They are called respectively the left and right index on the fuzzy random variable x. Below we will consider the class of fuzzy random variables x for which hold condition 1. For each fuzzy random variable x, indexes x minus and x plus are functions that are quadratically summable by omega product 0, 1. Let x minus of alpha and x plus of alpha this expression. A fuzzy number x with indexes defined by formula 3 is called a fuzzy expectation of a fuzzy random variable x. Let x alpha of omega is equal x minus omega alpha and x plus omega alpha interval alpha level of the fuzzy random variable x. Expectation E of x of fuzzy random variable x is number defined by the expression. We define a quasi-scalar product for fuzzy random variables x and y with alpha level sets x minus, x plus, and y minus, y plus by the formula. Formula 5. In this case, the quasi-norm of the fuzzy random variable x will be denoted by the formula this. Note the same properties 1, 5 hold for the quasi-scalar product 5 as for the quasi-scalar product of fuzzy numbers. Define the distance between the fuzzy random variables x and y from the class x with the expression 6. Expectation E of x and the fuzzy expectation x of a random variable x have the following extreme properties. First, for a given fuzzy random variable x with indexes x minus, x plus, the expectation E of x is the only solution to an extreme problem. D of x y tends mean. With the distance d is defined by the formula 6. Second, expectation E of x is the only solution to the following extreme problem. Rho x y tends to mean, where is the distance rho is defined by the formula 2. Third, the fuzzy expectation x of a fuzzy random variable x is the only solution to the following extreme problem. D x y tends mean. Define the covariance between the fuzzy random variables x and y with the intervals alpha level x minus x plus and y minus y plus by formula 7. This definition was used by Fenk in 2001. This definition is closely related to the quasi-scalar product 5 and distance 6 that we have introduced. The variance of a fuzzy random variable x is determined by the equality d of x is equal of x x. According to 6.7, the property is true. Where x is a fuzzy expectation on a fuzzy random variable x. Consider Chebyshev inequality. Lemma 1. For a fuzzy random variable x with a fuzzy expectation x and a given epsilon more 0, there is an inequality. 9. The proof uses the equality 8. Fuzzy random variables x1, x2 are called uncorrelated if cof x1, x2 is equal 0. Theorem 1. Law of large numbers. Let x1, x2 and so on be of pair of uncorrelated fuzzy random variables, and their variants are uniformly bounded. Then the relation is true. 10. The proof uses Chebyshev inequality 9. In contrast to the known results, we used metric 6. Consider the optimal linear approximation of the fuzzy random variable y by the system of fuzzy random variables x1, x2, and so on. We investigate the question of approximating a random variable y with a linear combination of form with real coefficients beta y by the distance minimization criterion 6. Consider an extreme problem with the non-negative coefficients beta I more than 0. 11. Lemma 2. Let us fuzzy random variables x, y be a quasi-orthogonal for I not equal z, and their quasi-norms is not equal 0 in addition. Let the condition scalar product y and xg more than 0. Then the problem 11 has a non-negative solution and a unique one. It has the form, this form. Theorem 2. Let the fuzzy random variables of the system X, Y be quasi-orthogonal for E not equal G, and all the quasi-norms not equal 0. Then the problem the distance between Y and the sum vector I xi tends to mean has a solution and a unit one. It has the form beta I is equal bi divided kappa I square. When proven theorem 2, we consider an extreme problem for a shift fuzzy random variable of the form Z is equal Y with C product the sum beta I xi, where C is a sufficiently large number. Then we use lemma 2 and the following special property of the distance 6 between the fuzzy random variables. Lemma 3. For any fuzzy random variables x and y and double y from x, the equality is fulfilled. We note that in contrast to the known results, the type of optimal coefficients in theorem 2 coincides with the Fourier coefficients in the system xy as if we use linear approximation methods in Hilbert spaces to find them. It is connected with our form of quasi-scalar products and the distance 6. We use reference. Thank you for your attention.
Thank you very much. So we have a lot of, not very a lot, but we have some time for questions. So please. Okay, so there is some question, please. Question.
Can I ask a question?
Yes, yes.
Thank you very much for interesting topic. I'm interested in this theme. Could you please, Dr. Khatskevich, could you please explain what is the sense of quasi-scalar product and what is use of it? Quasi-scalar product.
I belong to a new formula of quasi-scalar product 5.
in the very beginning of your presentation.
Formula 5 is a formula by the quasi-scalar product.
Yes, please.
And what about it?
What is the physical sense of this product? What is it about?
I understand.
So I see you have two variables, correct?
Yes.
And is it a kind of measure of correlation, isn't it?
Yes. Measure
I see.
Correlation, measure of correlation, it is connected with the correlation form with the formula 7, which used by Fermi, formula of covariation.
Tell me, please, is it somehow similar to clusterization, this problem?
Clusterization.
At some extent, I'm doing it, but I'm thinking maybe it is in connection somehow, no?
My English is bad, I don't understand. Sorry.
Владимир Львович, предлагаю переключиться на русский.
Да, слушай.
Спасибо большое. Извините за глупые вопросы. А можно мне прислать вот ссылку Econometric 2016, volume 42. Applied Econometric 216.
Сейчас я покажу. Вот, Шведов, 6 номер. Прикладная
This number 6.
42. Ну вот.
Is it open?
Да. Она и на русском, и на английском есть.
Хорошо. Я поищу. Сейчас я сфотографирую. Thank you very much.
Okay, thank you very much. So I think we should thank Vladimir once again, and now we're going to proceed to the third talk. Vladimir is here. Okay, Alexander, please share your screen.
Good day. Do you hear me?
So our next speaker will be Alexandr Rakitko, and he will speak about MDR method with forward selection, the topic which is connected with the topic of the talk of Professor Bulinski. Okay, please.
Okay. Do you hear me?
Yes, but we don't see your.
Okay, I'll share the screen right now. Second. Okay, so you see the screen, right?
Could you go to the full screen mode?
Surely, surely. Is it okay now?
Yes, thank you.
Okay, thank you. Well, okay. So my name is Alexandr Rakitko. Today I'd like to talk about the MDR method with forward selection. First of all, I'd like to thank the organizers of the conference for the chance to make this talk today. And I also would like to thank Alexandr Bulinski, Professor Alexandr Bulinski, for the discussions and the critical review of this research. Okay, let's start. Forward selection algorithms are widely used in various applications. They arise naturally when we need to find the subset of the reasonable, associated, meaningful factors among the set of the whole factors. So imagine that you have a lot of features which may be associated with the response variable. And the task is to find which of them is really associated. There are a lot of monographs and publications about this topic with the reviews of different feature selection algorithms. I would like to pay attention to the paper of Alexandr Bulinski and others in Open Journal of Statistics in 2012. And Pavel Iskov as well is the co-author of this paper, as I know. And the various algorithms are discussed there. For example, random forest, stochastic gradient boosting, and others. And my research is devoted to the development of the multifactorial dimensionality reduction algorithm. So, originally, this MDR method, multifactorial dimensionality reduction, was introduced by Ricci in 2001. Since that, a lot of different modifications and variants of this algorithm was offered, and in Gola 2016 you can find a so-called roadmap of such algorithms with more than 20 variants and modifications described there. In Bulinski 2012, the multifactorial dimensionality reduction algorithm with error function estimation was introduced. My current research is devoted to the development of this subtype of the MDR algorithms. It should be noted that now MDR method is widely used in various applications, especially it is popular in the genetic studies when we try to find the so-called epistudies, the interaction between factors which might be reasonable for the disease risk prediction. And you can find a lot of papers where this kind of algorithm help to find the new genetic associations with different diseases like Parkinson's disease, coronary heart disease, and others. Well, and it also should be mentioned that even now, the new versions of the MDR methods continue to be developed, and one of them is MDR method for stratified samples, which was presented by Bulinski and Khatskevich in 2017. Okay, let me introduce some notations and the main ideas of the method. As I already said, usually this method is applied in the genetic studies, so we can parameterize a person with his genetic and mental or lifestyle factors. So we consider X as the vector and Y as a response function. Both X and Y are random. And in many applications, Y is the disease status. So for example, Y equals 1 means that the person is, has a disease, and -1 means that the person is controlled. And XI is the so-called single nucleotide polymorphisms or genetic variance. Okay. So in more wide setting, X is a random vector with components xk taking values in finite set. In one of my papers, we extend this theory to the case when X is a continuous random variable. But here we consider the simple case with the discrete values. Okay, as I said, X takes values in the X set, and Y in more general set takes values in, it is integer, and takes values from -m to m. The main idea of the algorithm is to build the prediction function f, which try to approximate the true value of y. So we use f to predict y values based on x values. And we introduce the error functional, error of f, to measure the quality of this prediction. It is equal to the expectation of the absolute difference between random variable y and random variable f of x, multiplied by the penalty function psi of y, which works as a kind of weight to give more preference to certain values of y. Okay, as you can see, this error functional depends on the distribution of the vector x, y. So we need a kind of the statistical estimation of this kind of value. But before, I would like to describe the whole concept. We use not any function f, but we try to use the optimal. It is possible to calculate the formula for the f-opt, which is the optimal function, and it is the solution of the optimization problem, where we try to find the such functions f, which gives us the minimum of the error function. So when we get this f-opt optimal function, we can build the statistical estimation of it, FPA, where PA stands for the prediction algorithm. FPA with head is the estimation of the f-opt, which is billion using the sample. Psi head is the estimation of the penalty function psi, and error head is the estimation of the error function. To make these kind of estimations more stable, we involve the k-fold cross-validation procedure. So the core idea is the following. We divide our data set into k parts, k folds, and we use k-1 folds to estimate the prediction algorithm f hat PA, and we apply this build estimate to the other part of the data and make the prediction for it. And then we measure the error of the prediction, and we have the value of the error functional on the test data. And then we switch our folds and repeat this procedure k times, and receive k estimates of the error functional on the test data using the prediction algorithm, which was trained on the training data. After the average of such errors, and have our final more stable estimation of the error functional involving k-fold cross-validation. So here are two formulas. In the first formula, you can see how we can rewrite the error functional. And the second formula illustrates how we build the estimation. You can see that we use psi head and use the sum of indicators normalized by the number of the summands to approximate the probability. And we see the summation over k, which indicates the procedure of the cross-validation. Okay, so in the previous papers, the criteria for the convergence almost surely was established for the such kind of estimation. So we assume that for a good set U, we have the convergence almost surely of our prediction algorithm, and then we can formulate in terms of these kind of random variables the condition which is enough and which is necessary for the convergence almost surely for this kind of estimation of the error functional. So one more time, we involve k-fold cross-validation and we build on the subset of the data our prediction algorithm, and then we calculate the error functional on the rest part of data, and then we have such kind of convergence. It is not so straightforward theorem because these kind of permutations from default cross-validation gives us dependent random variables, so we have to deal with them. Okay, it's time to introduce the definition of the term significant. Assume that we have n features, n factors, and the dimensionality of the vector x is equal to n. And we assume that conditional probability of y given all features x1, xn is equal to the conditional probability of y given just subset of these features. Let's say it will be k1, kr. Such collection of indexes is called significant. So the main idea of this approach is to find this significant collection of indexes from the following theorem states that it is quite natural and reasonable to take as the significant collection which has the minimal estimation of the error functional and gives us an idea of how we can work with our data. We can try to choose the different subsets of the whole set of features. For each subset of indexes, we build the prediction algorithm and estimate the error functional of this prediction algorithm. Let's say it is f beta pa, and then we find the such beta, let's say it will be alpha with minimal, which is significant and has the minimal error functional value of for this prediction algorithm. And this theorem states that asymptotically we will be right. Okay, and the last result which we'll need in the future is the central limit theorem. In the papers of Bulinski and Rakitko, it is described and proven that we can introduce the so-called regularized estimators or regularized versions of the prediction algorithm, and then we can prove the central limit theorem, which states that difference between the theoretical value of the error functional and the estimated value using the cross-validation multiplied by square root of n, where n is the sample size in low to normal distribution as n tends to the infinity, and we can show that the limit variance is equal to the variance of the random variable v, which is shown here. Okay. In fact, as I said before, we deal with the dependent random variables due to the procedure of the cross-validation. But this kind of the dependence has a good property of the exchangeability. So in fact, we deal with the exchangeable random variables, and there is a big theory for this kind of random variables, and we, in a separate paper, we have proven the other versions of the central limit theorems, theorem based on the approach with exchangeable random variables. Okay, so the last thing I'd like to say before I formulate the theorem is the choice of the penalty function. In Velis 2007, the following choice was introduced, and it was explained why it is reasonable to use this kind of penalty function in several papers of Bulinski and others. And we use exactly the same penalty function in our study. Okay, the main problem of this approach is that it is computational inefficiency, because when the number of factors increases, the number of the collections, subsets of the factors to be tested increases dramatically. So we should offer the other kind of algorithm, maybe which is maybe less stable, maybe less good in its accuracy, but which is computational effective. So we try to apply the so-called forward selection procedure to find the significant collections from the data. What is the main idea? In the first step, we select a factor xi1, which has the minimal error among the all prediction algorithms, which were built using just one factor. And the next step, we consider the pairs, where the first element of the pair is xi1, and the second one is xi, where I takes values from 1 to n, except i1. And we select the second factor to this pair, which gives us the minimal error functional value for all pairs described before. And then we repeat this procedure r minus 2 steps and get the our significant based on our data set collection. It should be noted that here we assume that we know the number of significant factors, and this number is equal to r. In general, it is quite difficult to prove a kind of general theorems for this kind of algorithms. So we add additional assumptions about the distribution of the vector xy. Especially, we assume that x takes just two values, 0 and 1, and y, as before, takes two values, -1 and 1. We assume that y depends on exactly r factors, whereas r is less than n, and we assume the conditional independence of the components x of the vector x given y. It is the third condition. And it is easy to show that if we assume the following conditions, then we obtain the model of naive bias classifier. Yeah, here the short outline. We introduce the notation of theta vy. It is the conditional probability of xi takes values v given y takes value y. And we can rewrite the model as the logistic regression, and then the coefficients of this regression can be expressed using these thetas. Okay, without loss of generality, we can assume that our factors are sorted in the following manner. We take the first, we assume that the first factor is the most significant in this sense shown here, and factors r plus 1 and till n are not significant, and the corresponding coefficients in the logistic regression is equal to 0 for them. So in this, after this assumption, our goal is to find the right answer for our model is 1, 2, 3, and till R. So in fact, we would like to estimate the probability that our algorithm on the first step take the first factor as significant, on the second step the second factor, and so on. And as the final result, this algorithm takes first R factors as the significant collection. And the following theorem is proved. We got the lower and upper estimates for this probability, and you can see that when n, the sample size, tends to 1, this probability n tends to the infinity, this probability tends to 1. And more detailed formula is listed here. I would like to give you a brief description of the main steps of the proof. The first step, we decompose the probability that S1, the number of the factor which is chosen in the first step, is equal to 1. We decompose it into the production of the conditional probability, and we then consider each conditional probability separately. And for each conditional probability, we can describe the following in equation number 10, involving the probability that a certain estimate of the error functional is great for a certain subset of the factors greater or equal than the other value of the error functional for the other subset. And you can see that the difference is just the last factor, the factor which we add after case steps. We use the decomposition of the difference of these error functional values, and afterwards we can apply the Markov inequality to give of the estimation. We also use some facts which were proven before. For example, we use the fact that we have the convergence of the expectation, L2 convergence, and we use the fact that we have the assumptions of the criteria of the almost sure convergence. And these assumptions and the previous theorems guarantees that we can build this kind of the estimation for the probability. And in fact, the results of this theorem could be interpreted as the following. If we have the very basic, very simple model with the model of naive bias classifier, then our algorithm with forward selection gives us the result which we expected. Of course, it's not enough, I guess, and it will be better to prove the same theorem and to obtain the similar estimates for the more wider class of models. But that's what we have, and we can also express these coefficients c, k plus 1, these constants as the functions of theta of conditional probabilities from the naive bias classifier model. Here's the remark. Okay, so as a summary, we introduced the MDR method with error function estimation and with forward selection. And we show that in the model of naive bias classifier, the probability of finding the correct collection of significant factors with forward selection tends to 1 when the sample size goes to infinity. And finally, I have 5 minutes. I'd like to give you the motivation. Why do we need such kind of algorithms? You know that there are more than 7,000 of monogenic conditions like Tay-Sachs disease, hemochromatosis, and other diseases. And the property of such conditions is that just one mutation in the genome is enough to cause such diseases. But the most part of the deaths in Earth are devoted to the so-called multifactorial diseases or complex diseases, such as coronary heart disease, obesity, cancers. And the property of these kind of diseases is that a lot of genetic variants, a lot of single nucleotide polymorphisms contribute to the risk of the disease. For example, in the very first paper of Ricci, where the original MDR method was introduced, they considered the case of the breast cancer, and the problem was that there are a kind of sets of variants which might be genetic variants, factors, which might be very slightly associated with the response, with the disease, if we consider them separately. And if we consider this certain combination of the value of these factors, then the risk of the breast cancer increases dramatically. And the idea of this method is to find this kind of combination, this kind of nonlinear interactions, and so on. And one of the advantages of the MDR method with error function estimation is that is non-parametric, but one of the main drawbacks of it is that it is computationally inefficient. So this modification of this algorithm with forward selection is an attempt to speed up this algorithm, because you don't need to calculate the error functional value for all the possible combinations, but you just need to follow these steps, and the computationals are much more effective. And the model I described in this regarding the multifactorial diseases is the model of epistasis, and definitely for now we know, for example, that the heritability of schizophrenia is about 80%, and the non-genetic variants which were discovered using one-factor analysis explain less than 20% of the variation of this disease. And one of the hypotheses is that the missing heritability, so unexplained heritability, which we see, is explained by the epistasis as well. So in the future, we expect that, you know, that now in genetics, the most popular prediction model is the linear model, when you just sum up the genetic variants with certain weights. In other words, you use a logistic regression with betas from logistic regression, and it is quite simple, but it is not so accurate as it could be if we will learn how can we involve the non-linear interactions and the effects of epistasis into the prediction model. Really reasonable and valuable task in medical biological studies. Well, here is the list of selected publications. Thank you for your attention.
Thank you very much for the nice talk. Maybe we have time for one quick question. Is there any? Pavel Iskov wants to ask a question.
Yeah, I have a question. As I understand, you assume that the number of significant factors is known, but in my opinion, it's more interesting to consider the case where you don't know this number. And also there is quite a standard approach, path lasso logistic regression, to select the set of significant random variables. Have you done some simulation to compare the method, forward selection method, with this standard approach?
The first question, I totally agree with you that the assumption about the fixed and known number of the significant variables is too strong, and there are some ideas how we can deal with it. We can, for example, vary this value and see how the error functional increases or decreases with the different numbers of the factors involved in the model. And yes, the lasso is a really popular model, and it is fast enough. But the drawback of this model, as I see, is that it is parametric. It assumes a kind of linear dependence, linear regression. I tried to compare this to algorithms, but for now I didn't find the model which efficiently showed that one algorithm, for example MDR, overhead the lasso. So in general, the results of the experiment is the following. Usually they choose the right collection of the factors, but lasso works faster. But from the general understanding of the problem, there should be kind of the set of the model when the lasso fails, but this non-parametric method find the right kind of the significant collection, but I don't spend so much time to work on it.
Thank you.
Okay, thank you. So I think we should thank Alexandr once again. And now we will have a break until 20 minutes past 4, right? So 17 minutes break, and we will continue.
Дмитрий, на всякий случай сообщаю, что докладчиком последним будет Musoni Wilson.
Доклад мой называется «Отрицательная биномиальная регрессия в зависимости от дозы эффекта». Ну, сначала математическая постановка, а потом что получено. Итак, предположим, что у нас есть случайная доза U, вводимая в организм, и X – это нижняя граница, с которой начинается реакция организма. Если U меньше или равно X, эффект отсутствует. В противном случае, то есть когда U будет больше X, эффект присутствует. Таким образом, мы имеем бинарную случайную величину W, которая есть индикатор вот этого события U больше X. Итак, предположим, что у нас x1, x2 и так далее, xn – это независимые, одинаково распределенные случайные величины с функцией распределения f от x, а u1, u2 и un соответствующие независимые случайные величины, и они не зависят от x и, будем предполагать сначала. И вот эти u имеют неизвестную функцию распределения g большой от x и плотность распределения g от x, который будем предполагать больше нуля. Итак, мы имеем, вот сама величина x не наблюдается, а мы имеем наблюдение в виде пары, вводимые дозы u и есть эффект, нет эффекта. И проблема состоит в том, чтобы оценить функцию распределения вот неизвестной латентной случайной величины x. Для того, чтобы оценить эту функцию распределения, мы заметим, что если u и x независимы, тогда условное математическое ожидание, здесь можно показать, будет равно f от x. То есть f от x является регрессией вот этой случайной величины W. И таким образом мы можем оценивать регрессию в виде, используя ядерные оценки регрессии. В качестве такой оценки берется отношение вот двух статистик S2n от x, S1n от x, где S1n от x это фактически оценка плотности распределения G от x, ядерная оценка, а S2n от x это вот это ядро K, умноженное на дубль B. И вот это ядро K от x, оно, будем предполагать, ограничено, четная функция, не отрицательно, ну и интеграл у нее конечен, будем предполагать, равным единице, то есть K от x это вероятностная плотность. H называется ширина окна просмотра, и, как правило, мы ее берем константу умножить на n в степени минус 1/5. Такая ширина окна просмотра. Известно, что при некоторых условиях регулярности эта статистика состоятельна и асимптотически нормальна. Но у нее, правда, есть не нулевое математическое ожидание, а 1 от x, которое имеет вот такой вид. Сюда входит как плотность G, F и второй момент вот этого ядра K. Дисперсия сигма квадрат от x, она равна f от x умножить на единицу минус f от x, и здесь преднорма ядра K. Вот такой интеграл. Поскольку она у нас ограниченная, вот эта преднорма, она будет конечна. Вот эта оценка типа оценки Надара и Ватсона. Вот здесь приведен график нормального распределения моделируемого и оценка, красная, эта оценка типа Надара и Ватсона, а здесь зеленый, там осуществлялось еще немножко устранение смещения этого. Теперь, значит, рассмотрим так называемую минуточку. Так, значит, где это излагается, где это можно найти. В русской литературе у нас мало сведений о этой зависимости доза-эффект. Есть такая книжка Лорен Закс «Статистическое оценивание» в серии «Статистические методы экономики». И там есть параграф, посвященный этой дозе-эффект. Он небольшой параграф. И оценка там, оценка производится либо функцией распределения, либо квантиле. И там рассказывается, как оценить медиану этого распределения. В токсикологии она называется среднеэффективная доза и обозначается ЕД-50. Способ такой. Вы должны примерно знать, где у вас средние этой величины x, на этом уровне произвести 6 наблюдений, отступить от него право и лево на одинаковое расстояние, провести еще по 6 наблюдений и проводим так до тех пор, пока у нас будут встречаться нули и единиц. То есть там не должно быть сплошных нулей и сплошных единиц. А далее строим оцениваем прямую регрессию. И на оси Y выбираем 0,5 и получаем оценку медианы. Суть в том, что предполагается, что случайная величина X имеет нормальное распределение, а в окрестности этого параметра, первого параметра, она примерно прямая. Но в некоторых случаях надо находить оценки квантилей, скажем, 0,95, 0,5, а таких методов, в принципе, тяжело здесь предложить этот метод. Тот способ, который там предложен, он записан в стандарте для испытаний у медиков. Теперь рассмотрим биномиальную регрессию. Мы вначале предполагали, что U случайная величина, теперь будем предполагать, что она не случайна, и рассматриваем значение U и маленькое. При этом значении мы проводим n испытаний, n большое испытание. И одинаковое количество испытаний при каждом вот этом И. Будем предполагать, что вот эти УИ, они, сама величина расположена на отрезке 0,1, это не принципиально, вот, и УИ идут равномерно, это тоже не так уж принципиально. И рассмотрим сумму вот этих случайных величин W и G. Тогда вот эта сумма W и она имеет биномиальное распределение с параметром n большое и вероятностью Pi. Вот эта вероятность Pi, она есть значение функции распределения в точке I на n. Ну, оценкой максимум правдоподобия этой вероятности является частота. Вот. И в качестве оценки тогда мы можем выбрать вот такое отношение. Вверху будет стоять WI, это значение вот этой W большое, а здесь стоит это I от X. Это I от X, это вот значение вот этой ядерной функции в точке UI минус X и поделить на H. Ну и здесь вот этот множитель впереди масштабный. Вот. Так вот, в этом случае, в принципе, мы можем рассматривать и исходные бинарные величины W и G, но если поделим числительный знаменатель на n большой, тогда мы придем вот к этой такой статистике, и здесь WI, в отличие от бинарной величины, она уже может принимать, она принимает дробные значения. Вот. Теперь еще для медиков есть такая книжка, автор ее Урбах, она называется «Статистический анализ в биологических и медицинских исследованиях». Там рассмотрен еще один метод, этот метод Рида и Менча, оценивание вот этой функции распределения. Дело в том, что почему я, скажем, занялся модификацией Рида и Менча, потому что в 2000 году вышла статья в Вестнике Московского университета «Химия». Там Гуревич подвергал сомнению вот этот метод Рида и Менча. Я его излагать не буду, я просто расскажу о модификации вот этой самой статистики. Так вот, рассмотрим функцию h большое от x. Это интеграл от минус единицы до x k t. Значит, на отрезке минус 1, 1. И эта функция h от x, она равна нулю, если x не принадлежит этому отрезку. Рассмотрим первую статистику S1 n от x, имеющую вот такой вид. И вторую S2 n от x, имеющий вид. Здесь стоит единица минус W, и здесь единица минус h. То есть как бы с хвостов этого распределения накапливаются данные. Потому что идея метода Рида и Менча у них первоначально состояла в том, что если, скажем, наблюдается эффект при какой-то дозе U, то он будет наблюдаться и при дозе большей, чем вот это U. И рассматривается отношение S1 n от x, а внизу стоит вот S3 n от x. Значит, рассмотрим условия, при которых я изложу результат. Предположение на плотность F, G и ядро. Существует третьи ограниченные производные. И также существует третья производная ограниченная для ядра. Предположение на H. H сходится к нулю, но недостаточно быстро, и nh квадрат сходит в бесконечности. Вот. Значит, отсюда nh, она будет сходить в бесконечность. Вот в Вестнике Тверского университета был опубликован результат, который говорил о том, что если x и u две независимых непрерывных случайных величины с плотностями f от x и g от x, соответственно, то вот эта оценка, она асимптотически нормальна, вот, и нормирующим множителем является nh. Вот. Так вот, теперь мы можем рассматривать также случаи, когда u фиксированные, это так называемый фиксированный план испытания, Ну, а некоторые его модификации являются следующие. Предполагается, что U имеет равномерное распределение в точках единиц на n и так далее. Вот. Теперь перейдем, собственно говоря, к отрицательной биномиальной регрессии. Рассмотрим случай, когда U является не случайной, и при каждом значении U, значит, рассмотрим вот эту величину, имеющую отрицательное биномиальное распределение ZI. Вот. И при каждом значении U, K у нас задано будет, при каждом значении U мы проводим испытания до тех пор, пока не накопим m единиц. Вот. Рассматривается следующая статистика. Отношение, вот здесь стоит m, а здесь вот эта сумма, и это и от x, которые у нас уже встречались. Внизу стоит zi. Вот поскольку вот эта сумма, нормированная сумма, она сходится к единице, это можно показать, тогда можно рассматривать вот такую оценку. m поделить на, вот в знаменателе будет стоять вот эта величина. Но поскольку результаты асимптотические, оценку мы производим при n, то практика показала, что лучше использовать первую оценку. Показано, что при вот этих условиях, которые сформулированы, там были выше, эта оценка, она асимптотически нормальна, вот, а у нее дисперсия, вот здесь стоит преднорма ядра k в квадрате, здесь делить на m, вот то число, которое мы задаем, вот, а здесь стоит сигма 2 в квадрате. Вот это сигма 2 в квадрате имеет вид f квадрат от x на единицу минус f от x. То есть вот при значениях, которые лежат слева, вот это, конечно, дисперсия будет несколько ниже. Что делать, если справа? Справа мы можем вместо W рассматривать единицу минус WI и фактически копить не единицы, а нули до значения m. Вот. Кроме этого, значит, вот это асимптотическая нормальность при каждом фиксированном x. Кроме этого, показано, что вот эта оценка при соответствующем центрировании и масштабировании, она слабо сходится к броунскому мосту. Кроме этого, для оценки скорости сходимости используется метод Стейна для оценки вот этой скорости сходимости. Ну и здесь есть еще одна проблема, она состоит в том, что когда я рассматриваю статистику, она есть отношение двух статистик, и мы доказываем асимптотическую нормальность, то мы рассматриваем ее при некотором n. Значит, хорошо известно, что если я возьму отношение двух нормальных случайных величин стандартных с параметрами 0,1, то ее отношение будет иметь распределение Каши. Распределение Каши, как известно, унимодальное распределение. Если же я рассматриваю произвольное совместное нормальное распределение, у которых математические ожидания отличны от нуля, и дисперсии сигма-1 квадрат, сигма-2, ну, скажем, различны, и у них коэффициент корреляции ρ, то вот это отношение двух нормальных величин, оно уже может быть и не биномиальным, то есть при каждом n и при соответствующих соотношениях вот этих параметров я могу получать ненормальное распределение. Вот. И есть такая статья, вот здесь ее автора я привел, она у меня там в списке литературы есть. Так вот, там предложен метод построения доверительного интервала. Вот этот результат, который для нормальных распределений, он был получен в 1929 году. И они используют этот Феллера результат для построения доверительного интервала. Теперь, где используется вот эта зависимость доза-эффект? Ну, во-первых, для оценки среднеэффективной дозы, вот большинство лекарственных средств, она рассчитана на так называемую среднеэффективную дозу. То есть та рекомендация, которая есть, это вот среднеэффективная доза. В свое время пришел товарищ из медицинского института, и он предложил следующую ситуацию. Говорит, у меня два вещества. Одно, скажем, отравляющее у него вещество, а второе, ему надо рассчитать антидот, так называемый, то есть какое количество вещества нужно компенсировать для того, чтобы эффект от этого отравляющего вещества нейтрализовать. Вот это одна из ситуаций. Вот в статье, которую я приводил, известной Куперского университета, там в качестве оценки рассматривалась оценка возраста появления премоляров. Вот в английской литературе такой монографией по зависимости от дозы эффекта является книга Финни, автор. Она называется «Пробит-анализ». Вот там вместо того, чтобы предполагать нормальное распределение X, рассматривается логарифм этого распределения. То есть, когда мы отступаем от средней дозы вправо и влево, мы берем логарифм этих доз. Потому что достаточно быстро было замечено, что распределение вот этой величины X, оно несимметрично. Вот. Эта книга, она впервые вышла в 1947 году. Это первое издание было. В 1971 году вышло третье издание. Вот в этом третьем издании Финни привел пример, который он взял из одной статьи польских исследователей. И она была посвящена оценке так называемой возраста менархии. Вот, допустим, вас интересует время наступления какого-нибудь события, а человек это событие не фиксирует. Но вы собрали некую группу, пришли туда и просите их указать возраст, и произошло это событие или нет. То есть человек может знать, произошло это событие или нет, и вы производите оценку вот этого самого. Там речь шла о возрасте менархии. Вот. Известно, что вот этот возраст менархии для городских девочек, он где-то в районе 13,5, а для девочек сельской местности 14,5. Вот в качестве дозы выступает вот этот возраст, а в качестве эффекта, естественно, появилось событие или нет. Вот если же вот человек знает точно, когда вот это событие произошло, тогда здесь будет другая же ситуация, так называемая случайно цензурированная выборка, и для оценки функции распределения мы можем использовать оценку Каплана-Мейера. Вот тут еще, сейчас я укажу, забыл, значит, речь шла об оценке квантиля. Вот. В качестве оценки квантиля используется вот эта обратная функция для оценки, и при тех же условиях показано, что вот эта разность, она асимптотически нормальна. Ну, здесь вот стоит лямбда на единицу минус лямбда, f квадрат от кси. Это, ну, как бы вот если рассматривать центральный член эволюционного ряда, то, вот, значит, вот в качестве дисперсии выступает вот этот прав. Здесь еще преднорма H. Ну, вот у меня по докладу все. Так.
Да, большое спасибо. Так, у нас еще есть время для вопросов, в принципе. Да? Может быть, вопросы какие-то? Так, что, вопросов я, по крайней мере, не вижу. Никто рук не поднимает. Спросить ничего не хочет. Ну что, если вопросов нет, тогда давайте еще раз поблагодарим докладчика. И продолжим, соответственно, через 5 минут. Continue. So next speaker will be Johnny Wilson, right? So do we have our next speaker? Yeah, that's great. And okay, so maybe the first slide. So move on. Yes, please share your screen and start with the first slide, please.
Can you see my slide?
Yes, we see them, but could you please start with the first one? We see something in the middle. No? Oh, this is number 6, I think. Not number 1. Make the full screen, please.
Musoni, could you please go to the full screen mode?
I think you can see.
Yeah.
You can see?
Yes, but please speak louder or something else because we hear you not quite good.
If I do like this, you can see?
Yes, we see.
Okay, thank you so much. You can hear me? Or I can increase my voice, maybe, I don't know.
Yes, everything is good now.
Okay, fine. Thank you so much, member and organizer and participants. My name is Musoni Wilson. I'm a PhD student at the Tomsky State University in Siberia. As you can see on the screen, I have 3 authors, Zhanna, me, and Sad Tarima. And I'm going to be the reporter on this paper. So let's first of all give you a small research description of our paper. This work compare to, okay, I'm sorry, first of all, I should tell you the title of my paper is Minimum Variance and the Minimum Kullback-Leibler Mean Estimation with Known Quantile. So it is the main on this research is just to compare 2 mean estimators. First one is MV, which stands for minimize variance, and second one is MKL, which is to minimize Kullback-Leibler divergence. Both estimators are asymptotically equivalent. It means all the same, but normal and normal distributed, but differ at finite sample size. In this part, I mean, it is asymptotically equivalent, but because of the sample size, you can see the difference between among of them. But in the beginning, it is by convention, it is asymptotically equivalent and normal distributed. So in this, I have used Monte Carlo simulation to study, to see what is the higher, what is the low between MV and MKL. As I told you, this is minimum variance, and also this is minimum Kullback-Leibler divergence, mean Kullback-Leibler divergence. So in this 2 comparison, I have used simulations, and whereby I have done simulation of uniform distribution function, normal distribution function, and the exponential distribution function using my own algorithm, which I have been used in Java programming. As I told you, I'm in the faculty from mathematics and computer science. So in that result, which I have done, it shows the difference between among of them, which one is higher and which one is very low. So the objective of this research, let's say epsilon be a random variable with the fx, which is cumulative distribution function, the CDF.
Musoni, excuse me for interrupting. We see only the first slide with the university.
Oh my goodness. So what is the, you can see?
So now we see only the university. Yes.
No.
Oh,
See?
now.
Now you can see everything.
Yes.
But if I try to do this, you know, you can see again. You can see.
Yes.
You can see now everything.
Yes, we see your slide with the research description.
Yeah, thank you so much. I don't know, maybe it is my computer. I'm sorry for maybe. So I need to, so the research was just to compare mean estimators, which incorporate information about quantile, known quantile, whereby you want to compare the main research description, the main reason which you did in this paper is just to compare between MV, which is minimum variance, minimizes variance, and the MKL, which is minimizes Kurbach-Reb divergence. So in these two means, I have used both estimators are asymptotically equivalent and normal distributed. But the difference between among of them, it's the number of the sample size. So we are going to, what I have done is just to show you, according to the number of the size, when I'm increasing the size, there is a result. When I'm decreasing the size, there is a result. So to do that, I have used Monte Carlo simulation with my algorithm, which I have been done through Java programming, which I have constructed. So whereby my aim was to find out which is the higher mean squared error than others. So the result was MV has higher mean squared error than MKL in the majority of simulated scenario. This is what I'm going to show in the next slides. So the objectives of the research, let epsilon be a random variable, whereby we have f of x equal to cumulative distribution function, and we have as well x1 and x2 up to xn, which is a random sample of independent and identically distributed random variable. So in this slide, the main objective of this study is just to estimate an unknown mean, which is noted by the big A, Eps, which is equal to A as it is, with the use of the known quantile xq, so that f of xq can be q as it is given on this formula number 1 on this slide.
Sorry, I think we still see only your second slide.
Oh my. So maybe I can. Now you can see all.
Yes, now you know.
So let me maybe use this so that we can not. So I was talking about the objective of the research, whereby I was telling that let's suppose epsilon be a random variable, and the f of x equal to the p when the epsilon is less than equal to x. We are having the cumulative distribution function CDF, and also we have the some sample of independent, which is x1 from x1, x2 up to xn, and identically distributed random variable. The main objective of this research is just to estimate the unknown mean, which is the big A epsilon equal to small r, with the use of the known quantile xq, so that it can give this formula as it is noted on number 1. So if we go on the second, another slide, we are going to see this is the minimum variance estimator formula. This is the mean, which has been shown with given addition information and quantile, whereby we have a mean x power q1, which is having the following formula as you can see, but I should be different from j, as it is given on the formula number 2, whereby you can see xi is less than or equal to xq of the quantile. So minus q, as it is also xj should be less than or equal to xq minus q, the whole divided by q times I minus q. So this is the formula which is, it is clearly on this slide, whereby we have number 2. And then we have an unbiased statistic. So it is also variance, which is also given on the mean minimum variance estimator. This is formula which is belongs to the mean variance. So we can see the variance on the formula number 3, and you can see here on also the same on the number 4 with the given number n times variance of the mean. It is the algebra. So if this is also that was the for minimum variance, and this is for the minimum Karlbach-Leber estimator formula, which is, of course, I can call it 2 because this was 1. So to differentiate both, it is 2. So it is also given, but in this, R should be equal to 0, all R should be equal to capital N, as it is given on formula number 5, as it is written there here. And this R should be, of course, between, should be bigger than 0, and also this R should be less than N, capital N. So the formula to find out this R, small r, is summation of I, this is I, parenthesis, xi less than or equal to xq, so times the capital I. This is my algorithm which I have been used to find simulation on my algorithm which I have done in Java. So in this, as you can see, it shows in unbiased for 0, I is between 0 and n. And this is the formula which I have been used in my algorithm, as you can see on the number 7. This is for minimum Karlbach rate estimator. So if we go to the mean squared error, as you can see, it is also variance whereby you have the limit of n. As you can see, it is of course a big formula, but which is also on the number 8. As you can see, this I have been used in my algorithm to find out a simulation which we are going to see on the following slide. So for Monte Carlo simulation, which is the main focus, main objective of this research, this was for finite samples with constant 3 distribution. The first distribution was uniform distribution function, which is f of x equal to the capital U, which is represent uniform, of course, between 0 and 1, as you know, uniform distribution, it is variate between 0 and 1, x. Then we have the second one, which we are going to simulate. It is standard normal distribution function. Of course, it is capital F, x, which is equal to capital N between 0 and 1 as well. And of course, as you know, it is of x. And then we have exponentially distribution function, which is also f, but which is 1 minus exponent. As you know, this is a function of exponential minus x, which is x should be bigger or equal to 0. Of course, it can be 0, but also it can be bigger, means bigger than this. So to find exact result, which is occurrence, we have, in that I have used the Monte-Carlo experiment, used 100,000 resemblers, means it's like 100 times repetition, means 100,000 times, I can say in good way. So this was that. So what was then the output on that practically, so that we can, of course, understand very well what was the output. So the result which I found as output on uniform distribution function, which here I put as number 1, the result which I found was, as you can see, we have some graph whereby you have the quantile here equal to 10 and n equal to 30, as you can see. But if you see the horizontal solid, the word horizontal solid, it's this line from here up to here. So, and we have also this variance of solid, which is, of course, solid is this one. You can see. For the first one, it is going straight away, straight line. But for the second variance of the second MVKL, it is not going straight away. It goes, of course, kind of down. So for mean squared error for MV, which is, of course, 1, as I told you, it is circled marked. Circle market is this line, which is going on the top like this. And if we go to the mean squared error for the second MKL is dotted. You can see it is like this. It is also below. It's not going. It is low than the first one, as you can see. So in this is when n is equal to 10. Let's suppose n is equal to 30. You can see if n is equal to 30, the normal variance for the first is going to be, of course, horizontal. And of course, for the second one is going to be solid. Of course, it's going to be still down. Big difference. But let's suppose see mean squared error for the first one. You can see, yeah, it's not the same higher than the previous one, but as you can see, it is higher than the other one, which is on the second one, on the number 2. So between this uniform distribution function result, you can see, as long as we have n which is 10, of course, the mean squared error of MV, minimum variance, it is higher than when n is bigger. When n is less, the number of MV, it becomes higher compared with n is bigger. But the second thing here, we can give another conclusion. We can say that, of course, no matter what mean squared error of MV, it is bigger than MS E of now of 2. That is also, we can see, because we want to see the best one. This is in case of uniform distribution function. Let's see when it is normal distribution function. The same story, as you can see, if n is equal to 10, yeah, you can see the horizontal of variance 1 is, of course, still horizontal. But when it becomes of the second one with quantile, which is MKL, it is also less. The same thing like the uniform. Then when it comes about mean square error of 1, so you can see it is also kind of course, normal distribution function. It is having the curve like this, but it is also bigger than MSE of second one, which is this one, as you can see, the dots, which is here. So the same here, it is the same. Still, the mean square error of the first one is still bigger than the mean squared error for second one. But the main point here, it is if n is still bigger, small, the mean squared error it's become MV it become higher, but higher than when it is it depends upon on the changing of this of the number of size. So this is the same. If we go to the exponential distribution function, it is also looks like kind of the same, whereby the n, because n is 10, you can see still horizontal, it doesn't, but we are focusing a lot about mean squared error, which is of course this graph, which is higher. If you compare it with when n is 30, you can see it is very, of course it's higher, but if you see this and this is a little bit lower than this. So it means when n is less, the number, the MSE is higher. But if n is bigger, the MSE is low on the MV, mean variance. So if I can talk about the conclusion, the results show that Kohlberg divergence minimized led to smaller, of course it is smaller, mean squared error than the estimator based on the variance minimizers. Of course, as you have seen, you can conclude straight away that this Kohlberg divergence minimizers is very small, is smaller than the other one, which is MV. So conclusion which I have taken, asymptotically mean squared error of MV and MKL estimators of unknown mean modified by a known quantile are the same. Yeah, of course, final sample MSE of MV and MK estimators studied by Mota Carlos simulation for uniform, Gaussian and exponential. When you talk about Gaussian, it is normal distribution, the same name. MKL estimate showed smaller mean square error. Of course, we have seen according to the graph, and the more detailed study of final sample is prospective for the research. So these are the source of the, or maybe references, whereby I have I have checked some of the big publication paper and some of the very good publishers, which is very known, and also have used one of our another paper which have been published in Vienna. Also, so these are my presentation, and thank you for your attention.
Thank you very much. So we have time for questions. So please. So I don't see any raised hands. And so then I think we should thank the speaker once again and all the other speakers of this afternoon session. We will continue our section tomorrow. So everybody is welcome. And thank you everybody for coming. And so today.
Thank you so much.
Thank you. So we will continue tomorrow. Thank you very much.